Welcome to EPG Pathashala. We are looking at computer science courses. So, we are looking at computer networks. So, in today's module, we will be looking at routing which is used in the IP networks. So, specifically we will be looking at the distance vector routing and we will also look at the RIP protocol. Okay. So, we will start off with the difference between forwarding and routing. So, then we will look at the basics of routing algorithms and then we will look at the details of distance vector routing. And then we will also look at how this distance vector routing is used in the IP network, which is used as part of the routing information protocol, the RIP protocol. Okay. So, let us first understand the difference between forwarding and routing. Now, forwarding refers to selecting an output port based on the destination address and the routing table. That is, when a packet arrives, you look at the destination address and based on the destination address, you select an output port, right, and you send it on to that particular output port. That is forwarding. Routing, on the other hand, is the process by which this routing table exactly is itself built, right. So, the process by which routing tables are built are what are referred to as routing process. Okay. So, we talk about algorithms that are used for this particular process, which are the routing algorithms. So, routing versus forwarding is something we need to understand, though of course, many a times there is a tendency to use these two terms interchangeably, but there is a subtle or a clear difference between these two which we need to understand as network designers and network users. So, to understand that a little further, just look at this picture. So, I have a router here. So, at the router there are two things that will be there. There will be a routing algorithm which is running and there will be this local forwarding table. So, when a packet comes in, right, you pick out the destination address from that packet, you will check that destination address over here, right, among the range address range specified here, and based on that you will send it on to a corresponding output link. So, this routing algorithm, this determines the end-to-end path through the network, right. So, this is fixed based on how you reach the destination based on the end-to-end path information. Now, this information, this determines the local forwarding at this router. That is, at this router it has to be sent on this particular path, right, and that is it has to be sent out through a particular output link. So, that information is what is specified by the forwarding mechanism. Routing algorithm is the one that is responsible for identifying the end-to-end path throughout the network. So, if in the forwarding table, so if you look at information that is there in the forwarding table and the information that will be there in a routing table, okay, to understand the difference a little further. So, in the forwarding table, we know that it is used whenever the packet is forwarded, right. So, it must contain enough information to accomplish this forwarding function. So, what is the information that it should have? So, every row in the forwarding table would definitely contain a mapping from the network number, right, the destination network number to an outgoing interface and also some MAC information such as Ethernet address or whatever of the next hop. Because why do I need this? So that I can send it on to the layer 2 and that layer 2 will be able to deliver it to that particular next hop or the next node or whatever. Okay, so that is important. A routing table, on the other hand, it is built by the routing algorithm as a precursor to building the forwarding table. So, you will need to have routing tables in place before you can build the forwarding table. Okay, and generally this will contain information about the mapping of network numbers to the next hops. Okay. So, if you look at this the example of tables over here, so this the one that is on top is a routing table and the one that is below is a forwarding table. So, this routing table you can see will have some network address specified, so 18/8 whatever, right, and the next hop IP address is specified. On the other hand, if you look at a forwarding table for 18/8, it specifies which is the interface through which it has to be sent out, right, the interface 0 and the MAC address through which it has to be sent out. Okay. So, which means it would correspond to this IP address, but correspond to this IP address, this MAC address is also given, the mapping is already done, it is given. So, that when you send out on this IF0, you send it out, give it to your layer 2, specify this MAC address, your layer 2 will be able to deliver it to that particular interface, to that particular machine. Okay. So, that is the difference that you will normally find practically when you look at a forwarding table versus a routing table. Okay. Now, coming to the task of routing, right. So, forwarding is something that we have seen as part of IPv4. Now, routing is the task that we need to understand. So, routing as we said is all about selecting a path from a source to a destination. So, what are the goals of routing? Okay. So, the routing that we are doing, the algorithm that we are doing, that we need to come up with has to be efficient. So, what do you mean by efficient? It should support low delay, high throughput and so on, right. It should be scalable, which means that even if the number of nodes increase, number of routers increase, number of networks increase, your algorithm must be scalable, must be able to cope with all that increase in number. It should be stable. So, which means if you just found out a particular route Okay, I should not be changing that route frequently and saying that, okay, now I have a different route. Okay, so you should be able to identify stable routes, because that's important for the, again, for the efficiency of the network as a whole. It must be robust and it must be fair. So even if there are failures, it must be able to handle that, and it must be fair in the sense that from all sources to all destinations, you must have routes which are possible and which are of equal priority. Okay? These are things that we would like to have. Of course, if you need to give high precedence or high priority to a particular path or to a particular node, set of nodes, that should also be possible. Okay? But in general, like you to have these the goals that we just mentioned over here. Okay. And the way we normally go about doing this is by modeling the network as a graph. In order to find the route to go from any source to any destination, we model the entire network as a graph, okay, and identify this problem of finding a route, right, of finding a path from the from a source to a destination as the problem of finding the lowest cost path between any two nodes. Now, we know from our graph theory that the moment you have a graph, you can always find the shortest path between, or the lowest cost path between any two nodes. Okay. So, we basically need to find, suppose I want to find a path from C to F, I am looking at a path where the cost of the path is a least cost path. So, and we also know that the cost of the path will be equal to cost of all the edges that make up the path. Okay. So, you need to find out which are the edges and which are the what are the costs, identify the least cost path, and from that you should be able to find out the least cost path, and therefore the route to be taken from the source to the destination. Okay. This is the basic idea that is used, and you will see that most of the routing algorithms use this basic idea, this model of network as a graph. Okay. So, going a little further, so mathematically we represent graph G, right, as consisting of N and E. N is the set of the nodes which represent the set of routers, and E are the edges which represent the links. So, you have routers connected by links. You can easily understand why the network can be easily modeled as a graph, right, because we have routers and we have links between them. So, which directly corresponds to nodes and edges between them. So, you have E, which is a set of links, the set E, which consists of all the links that you have, right, the link between U to V, U to X, U to W, and so on, all the different links that are specified over here. Okay. So, this is basically how the network is modeled as a graph. Okay. So, now how do I come up with this least cost path? Okay, that is the next thing that we need to understand. Okay. So, what we normally do for this, okay, for this is that the cost of any link, right, x to x dash, okay, so you can represent that as C of x comma x dash, okay, and you assign some value to that cost. Now, this cost that you are specifying, okay, could be 1, indicating that it is just, you are just counting the number of hops that you have between a source to a destination, between two nodes, okay, or it could be inversely related to the bandwidth. So, which means higher the bandwidth, lower the cost, it will reach faster, or it could be inversely related to the congestion. If you have a higher congestion, you would actually have, you may not want to take that path, right. So, you may give a higher cost to that particular path and so on. Okay. So, you can determine the cost of each of these links, right, the cost that you are assigning to these edges based on various criteria, based on the criteria that you want to have to determine an optimal path from a source to the destination. Okay. So, we have various options that are available over here. Okay. And the cost of the path, okay, to go from x1 to xp, where you are visiting x2, x3, etc. in between, basically is sum of all the intermediate costs, right. So, C of x1 plus x1, x2 plus C of x2, x3 plus C of x3, x4 and so on, all the way up to C of xp minus 1 to xp. Okay. So, this is basically how the cost will be calculated. Okay. So, the key question is, what is the least cost path between any two nodes u and z? And the routing algorithm's job is to find that least cost path, right. So, we need a routing algorithm which allows us to find this path. When you talk of routing algorithms of this nature, there are different types of or classification that we can talk about. One of the fundamental questions that can be asked in coming up with a routing algorithm is it going to deal with global information or is it going to deal with local decentralized information? So, when I say global information, it means that I need to have a complete picture of all the routers that are there in my network. The complete network's picture must be available to me, and based on that I will identify the path to be taken from any source to any destination. Okay. So, you need to have information about the complete topology and the link cost information. So, there are algorithms which work based on this kind of information, which is called, they are called as link state algorithms. Okay. The link state algorithm is an example of such a global information based algorithm. Okay. So, the other option is a decentralized algorithm. in decentralized algorithm, or you can also call it as a local information algorithm, here what we do is every router knows information about its physically connected neighbors. It does not know information about others, but based on the information that it has about its physically connected neighbors, by iteratively getting information periodically, exchanging information periodically with its neighbors, right, it will construct the path to be taken from the source to any other destination. Okay. The distance vector algorithm is an example of this kind of an approach. Okay. So, this is what we will be taking a look at now, distance vector algorithm. Okay. So, we have these two options, global information based algorithms and decentralized algorithms. Now, both have their own advantages and disadvantages. We will take a look at these two things in detail. Okay. Another question that can be asked with respect to routing algorithms is it static or dynamic? So, what do we mean by this? So, static would mean that routes would typically not change, but you can in a sense say that it changes slowly over time. Okay. Routes will change slowly over time. Dynamic would mean that routes change very quickly, more quickly, and therefore, which means you need to have periodic updates, and whenever there is a link cost change, that should also be updated. Normally, we go in for dynamic mechanisms because we do expect routes to change and we would like to have periodic updates, and if any change is there in the link cost, that also should be taken into account. Okay. So, we will now look at the distance vector algorithm, right, which basically makes use of decentralized information, okay, and also handles things in a dynamic manner. Okay. So, if you look at the distance vector algorithm, the basis for the distance vector algorithm basically is the Bellman-Ford equation, which is something you would be familiar with from your knowledge of graph theory, and you have also studied this in your algorithms. So, in the Bellman-Ford algorithm basically is used to identify the least cost path from any node x to any node y. Okay. So, if you let dx of y indicate the cost of the least cost path from x to y, then dx of y is equal to minimum of c of x comma v plus dv of y taken over all v. Now, v is the set of all neighbors of x. So, for all neighbors of x, you find the cost from x to v plus the cost from v to y. So, c of x comma v is the cost to the neighbor v, dv of y is the cost from neighbor v to destination y. Okay. So, I find out basically the cost from all my neighbors to the destination y, add my own cost to reach that neighbor, okay, and the minimum of these will give me the least cost path. So, this is the basic Bellman-Ford equation. So, this is what is applied in the distance vector algorithm to find the least cost path to go from any node to any other node. So, as an example, let us look at this particular graph over here. Okay. So, you have x, y, z, u, v, w here, right. Now, clearly you can see that the distance between v to z, okay, distance of v to z, now there are many paths to go from v to z, but the least cost path, right, would be 2 plus 1 plus 2, right, that will be the least cost path. So, that will be 5. Now, similarly, dx to z, okay, would be 3, 1 plus 2, d of wz is again 3, right. So, these are things that we already can see very clearly, wz is 1 plus 2, 3. Now, if I want to say calculate the path, the distance between u to z, the cost bit of the path between u to z. So, du to z will be equal to minimum of, look at all the possibilities I have. From u I have 2 neighbors, right. From u you have, you can go 3 neighbors, you can go to v, you can go to x, and you can also go to w. So, minimum of c of u comma v plus distance from v to z. Similarly, cost of u to x plus distance from x to z, cost of u to w plus distance of w to z. So, all the 3 neighbors we have taken, and we are looking at the cost through each of these. So, what will be the cost? U to v is 2 plus cost of v to z is 5. So, 2 plus 5. The next one is 1 plus 3, okay, and u to w plus wz is 5 plus 3, that is, okay. So, minimum of these, you can see 2 plus 5 7, you got 1 plus 3 4 and 5 plus 3 8. So, minimum is 4. So, this will be the least cost that we have. So, the path that we should be taking will be through u, right, u to x and x to z. So, that is the path that you take. So, the node which is achieving this minimum, right, that will be chosen as the next hop in the shortest path, and that is what will be used in the forwarding table. Okay. So, this is the basis of our distance vector routing algorithm. So, how do we actually exchange this information, how do we get this information and so on. So, here we saw this graph and we could easily identify all this information, but as part of an algorithm, how can this actually be implemented? Okay. So, if you look at this, what every node basically does is it maintains something called a distance vector. So, this distance vector basically says from x, right, from the node x to y, where y belongs to n. N is the set of all nodes, right. To all the nodes it maintains its distance. So, we maintain this as a vector, okay. And every node x knows the cost to its neighbor, to each of its neighbors. So, C of x comma v is known to it, okay. And it also gets its neighbors' distance vectors, okay, by exchanging information, and it maintains that information as well and uses both this information to come up with the least cost path that we just talked about, okay. So, this is how it will do, alright. So, now, the key idea is from time to time each node will send its own distance vector estimate to its neighbors. Initially it will not have information about everybody, it will only have information about its neighbors, but similarly its neighbors will have information about their neighbors. So, by exchanging information between neighbors, it slowly picks up information about neighbor's neighbor, their neighbors and so on, okay, that is the idea. So, when x receives a new distance vector estimate from the neighbor, it will update its own distance vector using the Bellman-Ford equation, okay, which is that again just as what we saw just now, right, minimum of C of x comma v plus dv of y for each node that you have. So, for each node as it gets new information it updates its vector, okay. And under natural conditions over a period of time you will find that dx of y will converge to the actual cost of the network, that is all the elements that are there in your vector will start corresponding to the actual cost to the various nodes that are there in your network, okay, that is the idea. So, now this whole process is basically an iterative process and it is an asynchronous process. So, each iteration, okay, is caused basically by two things. One, there may be a change in the local link cost, okay, something could have changed with your local link. So, that will change the vector, or you could get a update message from your neighbor. Something could have changed at the neighbor and therefore he could have sent you a distance vector update message. So, in both these cases an iteration will be triggered, okay, and the whole process is distributed because each node notifies neighbors, right, its neighbors, and it does so only when its distance vector changes, okay, and those neighbors then notify their neighbors and so on, okay, if necessary, okay. If there is a change in their information based on the information it gets from one node, then it will inform its neighbors and so on. So, at each node basically what will happen is the following. So, it will wait for either a change in the local link cost or a message from the neighbor. When there is any change, it will recompute the estimates, right. When it recomputes the estimates, right, if the distance vector to any of the destinations has changed, then it will notify the neighbors. So, and this process will repeat. Now, this happens at each node. So, you can see that in a distributed manner, all the nodes, right, will pick up the correct information, they will converge to the correct information, okay. This is the basic idea of this distance vector algorithm. So, we take a look at an example. So, let us say we have the simple network here consisting of 3 nodes x, y and z. Okay, distance here is 2, here is 1 and it is 7 here. So, now initially the node at x will have information only about y and z, right. X to x is 0, y it has a distance of 2 because its immediate neighbor, z distance is 7, immediate neighbor. Similarly, and information from y and z has not got anything, so it sets all that information to infinity, the distances are set to infinity. Now, similarly at node y, the table at y indicates its distance to x and z, x is 2, 0 to y and 1 to z, other information is set to infinity. Similarly at node z, 7, 1, 0 is the information that it has as part of its distance vector, other distance vectors are set to infinity. Now, this information 0, 2, 7 is sent both to nodes y and z. Similarly, 2, 0, 1 of y will be sent to both x and z, right. So, like this you will have this exchange of information taking place. So, let us look at one exchange and see exactly how updates will happen. Okay. So, let us say at x I am receiving 201 from y and I am receiving 710 from z, right. These are two nodes that I have, two vectors I have received from y and z. Now, when this happens, my 027 that I have, right, is there a change that is going to take place to the values that I have over here? That is what needs to be determined. So, now what is the cost to y from x? Cost to y will be minimum of c of x comma y plus d of y comma y comma c of x comma z plus dz of y. Now, what is minimum of c of x comma y? X comma y is already 2 and y to y is 0, right. The other option I have is to z, right. X to z is 7, okay, and z to y is 1. So, 7 plus 1, 8. So, I have 2 and 8, the minimum of these two is 2. So, this information that will be written here is 2. So, cost of x to y remains at 2, there is no change in that information. But if you look at the cost to z, here cost to z is minimum of c of x comma y plus d of yz, comma C of x comma z plus d of zz. So x comma y is 2. Now distance from y to z is 1. So 2 plus 1. The other is 7 and 7 plus 0. Right? So if you compare 3 and 7, 3 is smaller. So you will see that z gets updated, the distance to z gets updated to 3. From 7 it has changed to 3, which means it has found that there is a shorter path than its direct path, which is through y. Okay? So that information is obtained in this exchange. So similarly, at every node, right, this kind of exchange will take place. So you can see the various exchanges that would take place here. There will be a change at each of these, and periodically, and because this value has changed here, right, similarly there will be no change in y, but there will be a change again in z, because z also you will be able to reach, from z you will be able to reach x through y. So here there will be a change and here there will be a change. So both these changes now will be sent to their neighbors, and you will see that in the third exchange all of them have got the correct information, right. So this is basically how the distance vector algorithm works. So just to give you another example of a slightly larger network, the only difference here is we have taken the costs of each of the edges to be 1, all are unit costs. So you can see that when you start off at A, for instance, A is connected to B, C, E and F. So its cost to B, C, E and F are set to 1, all the others are set to infinity. A to A of course is 0. Similarly, you will have the initial information for each of the, at each of the nodes. Okay. Now, the initial routing table at node A will be like this, right, showing just its cost to its neighbors and who the next top neighbors are. Okay. And the final routing table, after it has got all the information, it will have this updated cost and the updated next hop information. Okay. This is basically how it will be. Okay. So similar thing will happen at each of the nodes, and you will see that this will be the final destination that you get. Now you could actually work, I would urge you to work out this complete graph, right, the details for this graph, and arrive at this destination table. It will be an interesting exercise to understand how this whole thing basically works. So now we talked about this situation very nicely where everything converged very easily. Okay, but when links fail, there could be a possibility where things don't really converge so quickly. Okay, so we'll take a look at a case where it converges. We'll also take a look at a case where it does not converge so quickly. Okay, so let's look at this first example. So let's say I have this graph here. Let's say for instance the link between F to G has failed. So what will happen, F and G will both immediately identify that. So F will set its distance to G as infinity, okay, because that value has changed, it will send an update to A. Okay. So now what will A do? A will set its distance to G to infinity because it is using F basically to reach G. So its information also will be changed to infinity. Now A will receive periodic update from C with a 2-hop path to G. Now C can reach G through D. So C will send a distance of 2 to G, and that information that reaches A will allow A to set its distance to G as 3, right, because it can now reach it through C, and it will also send that update to F because something has changed here. So it will send this information to F. Now F will decide that it can reach G through in 4 hops via A. So it will make that update. So you can see that in about 2 or 3 exchanges, F gets to know that there is an alternate path to reach G, right. So this is a very nice situation. Now we look at a not so nice situation, okay, a slightly different circumstance for instance. So let's look at this case. Now same network, but let's assume that A to E link fails, okay, so the link from A to E goes down. Now look at what happens here. In the next round of updates, right, A will advertise a distance of infinity to E, okay. Now, but at the same time, B and C, right, both B and C could advertise a distance of 2 to E because already they have distances of 2 to E. Of course, they go through A, but without that knowledge, they can always send that information. Now, depending on the exact timing of events, look at what could happen. Okay, node B, on hearing that E can be reached in 2 hops from C, will conclude that it can reach E in 3 hops and advertise that information to A because it got some information from C, right, not from A. From A it got a distance of infinity, but from C it got a distance of 2. So it thinks it can reach E through C in 2 hops and sends that information to A. So now A will conclude that it can reach E in 4 hops and it will advertise that to C. So you can see that there is a kind of a circular thing that is happening over here. Okay. Node C now will conclude that it can reach E in 5 hops, okay, and the process will continue like this. So B now will think it can reach in 6 hops, A now will think it can reach it in 6 hops or 7 hops, and the whole process will continue. And the cycle will keep on continuing until the distances reaches some large number, right, which can be considered to be almost infinity. Okay. Now this is called the count to infinity problem. Now this is a problem that can affect the stability of the network. So this count to infinity is a problem that we need to tackle in the distance vector routing algorithm. So this problem is tackled in 2-3 manners. Okay, one is we normally use a relatively small number as an approximation of infinity. So you use a value normally which is about 16, because you don't expect number of hops to get more than 16. So you treat 16 as your infinity. So the moment it goes up to 16, you treat it as infinity. Another solution that is also provided is called as a split horizon solution. So what you do here is, if a node is sending a routing update to its neighbors, it does not send those routes it learned from each neighbor back to that neighbor. So I have already learned something from you, I don't give that same information back to you. Okay, for example, if B has the route E to A in its table, it knows that it has learned that information only from A. So it can't give back another information back to A saying, okay, that whenever it sends routing update to A, it does not include the route E comma 2 in that update. Okay, that way you can kind of solve this problem partially. There is also a stronger version of split horizon which is called as split horizon with Poisson reverse. Now here what happens is B will actually send back the information, but it will put negative information. For example, it will send the route as E comma infinity to A. So it says that my distance is infinity, so that definitely that route will not be chosen. Okay, so these are some solutions that are used for this particular problem. Okay. This distance vector routing protocol is what is actually used in the routing information protocol. Now there are many versions of RIP, V2 and NG and so on. So the RIP protocol is a very simple direct implementation of the distance vector routing. It uses a hop count as the cost metric, and you can go up to 15, and it restricts the size of the network to 15, and periodically routing messages are exchanged about every 30 seconds by means of advertisement messages, and each advertisement will consist of up to 25 routes. So the format of this is again very simple. You can look at what we have here. You will have a command, a version which tells you what version is it and so on, and then you have information about the address, the address prefix, mask of that network, right, whatever mask, that might be a CIDR mask, it may be a subnet mask or whatever mask, and the distance to that network. Now the family of net specifies that it belongs to the IP family, or it could belong to any other family as well, right. So the family of the network, the address, mask and distance. Similarly for the next network, network 2, what is its address prefix, what is the mask, what is the distance and so on, right. So every router, for all the networks that it is connected to, it will give this information, and this information will be exchanged among the different routers. And once they exchange this information, using the distance vector routing algorithm that we just saw, they construct the graph, they find out the shortest distance, and they identify the path to be taken, and they update the routing tables, and based on that they update the forwarding tables. So this is the crux of the distance vector routing protocol and the RIP protocol. So to summarize, we have looked at 3 things, right. So we looked at routing versus forwarding, we looked at what routing algorithms are expected to do, how the graph abstraction helps us to identify the route, and we looked at the distance vector routing algorithm. So we looked at the count infinity problem in that and its solution. So we also looked at how RIP is a simple implementation of the distance vector routing algorithm. Thank you.